Guys, welcome back to my YouTube channel, and today we are going to be looking at a question on fluid mechanics. So please do so well to subscribe to this channel. So we're going to be looking at a question on continuity equation. They said we should we should prove the continuity equation. Now they said consider a region of space filled with a moving fluid. Let the density of the fluid at point xyz at time t be this and this, and let the particle move instantaneously at a point xyz having a velocity vx, vy and vz respectively in the direction of the coordinate axis. By considering the flow through the boundaries of small dimension change in x, change in y and change in z, show that the components satisfies the equation. So now basically we are going to be assuming that the equation is an the fluid is an incompressible fluid, meaning that at the pressure at all points is equal to zero. And also meaning that the velocity, the density at every point during the motion of the fluid, or at every point, will be equal to zero. So now let's get down to proving the equation. So basically, before we start proving the continuity equation, since we are asked to prove the continuity equation following along the point x, y, and z axis. So we are going to be assuming a Cartesian plane. So now this is a three-dimensional plane here. This is a cuboid. So we're going to be assuming the fluid flowing through this cuboid, flowing in and out of the faces of or in and out of this cuboid. We are going to be assuming the fluid flowing through this face A, flowing into this face and out of it, or either flowing into this face and out of it, or flowing into this face and out of it, in three-dimensional plane. So basically we are going to be considering the three direction x, y, and z. So now let's start. Now let's assume that the equation, since we are given the velocity, let the velocity be vx, vy, and vz. So let the velocity be vx, vy, and vz. So now basically we are going to be assuming that we're going to be assuming the rate of mass flow of the fluid, meaning that you're going to be taking the rate of mass flowing into this particular phase, into this cuboid, then out of it. So now how do we get the formula for our rate of mass? We know that the formula for my density is equal to mass over volume, right? So now basically let me make my mass subject of formula. So my mass is equal to density times volume. Remember, we are asked to prove the continuity equation. So my mass is equal to density times volume. So now let me splitting this my volume. I have density times area times length or distance, because they both have the same unit. So now since I'm looking for my mass flow rate, the rate of flow of my mass per unit time into this phase, I'm considering this phase A, B, C, D at first, into this phase and out of it. That is the formula I want to calculate. So the rate of mass, since it's mass per unit time, dividing both sides by time, so I can eventually say my density is equal to area, distance over time, give me my velocity. So this is the formula I'll be working with. So I can basically say my rate of mass flow through this phase will be equal to the density times the area of phase A, B, C, D times the velocity. Now area of this phase A, B, C, D, you know that they've given us the dimension here. They said assuming the dimensions along all directions are the x, the y, and the z. So basically on this face here, you know the dimension along this plane is equal to the dimension along this plane because it's along the y-axis. So the dimension on CD is dy. So it will be length times breadth, because we are considering just this face. So it will be what? The length of this face times the breadth, which is equal to dy times dz. Times now the velocity along this horizontal plane we are given as what? Vx. So represent it as Vx. So now we move to our next step. We now flowing through this particular phase into this cuboid. We are going to assume that the fluid will gain an extra magnitude of mass flow rate. What am I trying to say? Now flowing into this particular figure, there will be a gain in mass, and flowing out of it, you have a new mass flow rate. It's just like flowing a particle flowing through a pipe with with a different area. For assuming the initial area flowing into a pipe with a different area, coming out with a different flow rate due to the difference in the size or diameter of the two pipes. That's actually what we are actually considering here. The fluid flowing into this particular phase, gaining a particular mass flow rate and flowing out of it. So let's assume that our gain in mass flow rate, gain in mass per unit time, since it's a very small quantity, it will be change with respect to x. Remember, we are considering the horizontal direction of this with respect to x. So now, when the particle is flowing out of this particular phase, EFGH, it will be flowing out with a new mass flow rate. Now we can say the new mass flow rate M2 is equal to the initial mass flow rate, which is this, plus the gain in mass flow rate. Gain in mass flow rate. So now, how do we go on about this? So my new mass flow rate is equal to my M1 is equal to what? My density times the y times the x, sorry, the z times vx plus the gain the x of density times the y times the z times velocity the x. So we can basically assume this is called fluid efflux. Fluid efflux. And this will be my fluid influx. So basically, if you are given a new mass flow rate and an initial mass flow rate initially flowing through this phase, and the final mass flow rate flowing out of it, we can calculate our gain in mass flow rate. Then we can say our gain in mass flow rate, let's consider it to be change in m, is equal to fluid efflux minus fluid influx. So my gain in mass flow rate is equal to d, we are just writing this, d dy times dz times vx plus change the x of density times dy times dz times vx respect to x minus my fluid influx, which is this. This is my fluid influx, which is equal to density times change in y times change in z times vx. So basically this will cancel out this. Then we are having my gain in mass flow rate to be d dx density times the dimensions or the area, then times the velocity, or with respect to x. So now basically we have actually proven the gain in mass flow rate, when the particle is inside this cuboid. So now then we can say that despite or in spite, then we can say that if the fluid is flowing towards the y direction, that is, if the fluid is passing through this phase and out of this upper phase here, then we can say the gain in mass flow rate, the fluid will gain, because it will be equal to change in d dy of density times, now the area of this particular phases. Remember, the area of the upper phase will be equal to the area of the downward phase. So the area of the upper phase having the same dimension, you know that this upper phase here, the dimension here is dx, dz. Then this upper phase, then the length here, the dimension is what? Dx. So the area there along the y direction will be the x times dz times my velocity along y direction, which we are given to be vy, will be equal to times vy with respect to dy. And the same goes for dz. The same goes for the z direction. So it will be d dz times density times dy dx times the velocity, or with respect to z. So Now, given this is the gain in mass flow rate at all direction x, y, and z. Now, moving further, we can say that since the mass flow rate, since the mass is equal to density times area times length, we can basically just call this volume. So area times length. Since the mass is equal to density times area times length, then we can say this gain in mass flow rate at all direction is also equal to me saying that given my mass m equal to density times area times length, my gain in mass with respect to time, that is gain in mass with respect to time, I can basically say all this here can be equal to my gain in mass with respect to time. Yes, because this is my mass flow rate. Like I can say this, I can sum up that this my gain in mass flow rate at all direction. If I differentiate my formula for mass with respect to time, I should have the same value of this gain in mass flow rate if I sum it up at all direction. Meaning that if I calculate my gain in mass flow rate with respect to time, I should have the same value as when I sum these three values up. So my gain in mass flow rate with respect to time, I can say d dt times density times area which is length, so basically area times length, which is equal to volume, right? So volume of a particular face there, or volume of the cuboid is what? Length times breadth times height. So now let me apply it. So the total gain in mass flow rate, total gain in mass per unit time should be equal to d dt times density times the volume. So now let's move on. My total gain in mass flow rate, which be add summing this and this, we have change in this with respect to x times density times dy times dz times vx with respect to x plus d dy plus rewriting this. So basically, right, summing up these three value of gain in mass per unit time along the xyz direction, equating it to my general mass flow rate or my total mass flow rate. So I can say this plus this plus this equal to this. And that is exactly what I have written here. So let's continue proving. So now I factor out. Now if you look at this particular equation, you see that the dimensions along those cuboid are actually in common. Now this is dx dy dz, this is the x dy dz, this is the x dy dz, all equal to the x dy dz. So I factor out the volume. So factoring out the volume, I have change in x, change in y, change in z, open bracket, d dx times density vx plus d dy times density vy plus d dz, supposed to be z, times density vz, all equal to d dt times density, change in x, change in y, change in z. So we all know that this will cancel out. So I'm left with d dx times density vx plus d dy density vy plus d dz times density vz equal to change with respect to t of my density. So this is what I'm left with. So factoring out my density, because density is common here and density is common here, factoring my density out, I have this open bracket, changing this with respect to x of my velocity, differentiating the velocity with respect to y, plus this with respect to my velocity along the z direction equal to this dt of my density. Now, for an incompressible fluid, remember that's what we assume to be. It is an incompressible fluid. So for an incompressible or steady fluid, its density or velocity, its density at all points must be the same. So taking the change in density with respect to time will give me 0. So my d dt of my density it will be equal to 0 for incompressible fluid. So I can basically say d dx vx plus d dy is my density, vy plus d dz vz all equal to 0. So basically, if I divide both sides by density, I have d dx vx plus d dy vy plus d dz vz equal to 0. So this is my continuity equation along a Cartesian coordinate. Basically, we can have two kinds of continuity equation, along the Cartesian coordinate or along the polar coordinate. So basically, this is my continuity equation along Cartesian coordinate. So thank you guys for watching, and please subscribe.